সৌরভ কিরকম আছো?
এই তো ভালো আছি। আপনি কেমন আছেন স্যার?
আমিও ভালো আছি। হ্যাঁ, তো থ্যাংক ইউ ভেরি মাচ। হ্যাঁ, ডিরেক্টর আসছেন,
শিওর।
তো ওনাকে আমি দিয়ে দিয়েছি, লিখিত পাঠিয়ে দেওয়া হয়েছে। হ্যাঁ,
হ্যাঁ হ্যাঁ হ্যাঁ।
উনি খুবই উৎসুক যে উনি ইন্ট্রোডিউস করবেন। হ্যাঁ,
আচ্ছা আচ্ছা।
ইয়েস, ফুল স্ক্রিন না, আপনি যেভাবে আছে সেভাবেই রাখুন। ইউ কান্ট মেক ফুল। ম্যাডামের সঙ্গে কথা বলছিলাম।
আচ্ছা আচ্ছা। ম্যাডাম কেমন আছেন?
ম্যাডাম ভালো আছে, স্ক্রিনে আছে।
হ্যাঁ, দেখতে পেয়েছি।
Madam, you can talk to him. Just switch on your mic. It's still mic টা
হ্যালো।
হ্যাঁ হ্যাঁ ম্যাডাম কেমন আছেন?
হ্যাঁ, ভালো আছি। তুমি ভালো আছো?
এই তো চলছে।
তোমার
বেশ ভালো, দেখা হয়ে গেল।
হ্যাঁ,
অন স্ক্রিন হলো।
অনেকদিন পর দেখলাম, ভালো লাগলো দেখে।
তোমার সব খবর ভালো তো? সবাই ঠিক আছে?
হ্যাঁ, সবাই ঠিক আছে। আমার রিসেন্টলি একটা বেবি হয়েছে, স্যারকে বলেছিলাম।
ইজ ইট বয় অর গার্ল? আরেকটা তো ছেলে না?
আগেরটা ছেলে, হ্যাঁ একটা ছেলে। হ্যাঁ ছেলে, এটাও ছেলে।
ছেলে।
আমাদের 4টে নাতি।
আচ্ছা আচ্ছা, দারুণ তো।
তোমার এদিকে আসার এখন কোনো প্ল্যান নেই না? একটু সময়ও বাজে যাচ্ছে।
আসলে ওটাই আমরা আসতে খুবই উৎসুক, বিকজ মানে 2.5 বছর প্রায় হতে চললো বাড়ি যাইনি। মানে 2 বছর বেশি হয়ে গেছে, মানে কলকাতা আসিনি। ফার্স্ট চান্সেই যখন টাইম পাবো আর কি, ভ্যাকসিনেশনটা হয়ে গেলেই আমরা চলে আসবো।
হ্যাঁ, আমাকে বয়ধান বলেছিলেন উনি লেকচার দিবেন এখানে, আমি ওনাকে বলে রেখেছিলাম, কিন্তু প্যান্ডেমিক হয়ে গেল।
হ্যাঁ
হ্যাঁ, তখন ওই ওয়েবিনারটা ভাবতে পারিনি।
হ্যাঁ,
উনি আস্তে আস্তে এজড হয়ে যাচ্ছেন। ওনাকে ওই তোমার ইনফোসিস প্রাইজের সময় দেখলাম
হ্যাঁ।
ছিলেন। হ্যাঁ, তো
আর উনি খুব একটা কমফোর্টেবল নন এই ভিডিও ইয়ে মানে টক দেওয়া বা এটসেট্রা, আমার মনে হলো দেখে আর কি আমার।
হ্যাঁ, রেকর্ডেড টক ছিল, ইট ওয়াজ ভেরি ক্লিয়ার।
হ্যাঁ।
ওকে, তোমাদের ডিপার্টমেন্টে 4জন ইন্ডিয়ান আছে? মানে সৌন্দররাজন আছে আমি জানতাম।
সৌন্দররাজন আছে। সৌন্দররাজন অরিজিনালি ইন্ডিয়া থেকে। রবি বাকিল তো ইন্ডিয়ান বর্ন নয়, মানে
ও আচ্ছা, একটা লেডি আছে কি?
একজন জেগো অ্যাসিস্ট্যান্ট প্রফেসর একজন আছে, কিন্তু ইয়ে নয়, মানে ফ্যাকাল্টি না, মানে ওই পোস্ট ডক। সেও ইন্ডিয়ান বর্ন না। ইন্ডিয়ান বর্ন একমাত্র আমি আর সৌন্দররাজন, দুজন আমরা। মানে
সৌন্দররাজন তো এখানে আন্ডার গ্রাজুয়েট অব্দি পড়াশোনা করেছে। আন্ডার গ্রাজুয়েট অবধি করেছিলেন শুধু? না, আন্ডার গ্রাজুয়েট না, আন্ডার গ্রাজুয়েট ওই বাইরে পড়েছে।
আন্ডার গ্রাজুয়েট মিশিগানে বোধহয়, মিশিগানে আন্ডার গ্রাজুয়েট করেছে। মিশিগানে বোধহয় আন্ডার গ্রাজুয়েট করেছে।
হ্যাঁ, আন্ডার গ্রাজুয়েট এখানে করেনি, ওই স্কুলে পড়েই আর কি। ওই is one of the fantastic effect of NBHM, বুঝেছো? He attended, he came in touch with Balu and various people, and so because that NBHM has done a lot of wonders. আমি যখন রিসার্চে ঢুকেছিলাম তখন শুধু ISI আর TIFR, that too disjoint. কিন্তু এখন তো অনেক ছড়িয়ে গেছে ম্যাথমেটিক্স, অনেক ইনস্টিটিউট হয়ে গেছে।
হ্যাঁ, অনেক অনেক হয়েছে তো।
আমি মঞ্জুনাথ, মানে কি মঞ্জুনাথ, এদের ইমেল জানতাম না, আর এত লেট বেরিয়েছে যে আমি কাজ করতে পারিনি।
হ্যাঁ, না না, ঠিক আছে।
কোত্থেকে? ফ্রম হোম। ওকে, তাহলে আমি চুপ থাকছি। একটু চুল বেশি পড়ে গেছে।
একটু বেশি পড়ে গেছে, হ্যাঁ।
অ্যাডমিট হলেই হবে। হ্যাঁ, যতটা পারে। আমি এখানে সুযোগ পেয়ে রিটায়ারমেন্টে পড়ে বেশ।
হ্যাঁ, ভালো তো, দারুণ।
And I'm very active in mathematics here. সবাই উৎসাহে একদম জবরদস্তি ম্যাথমেটিক্স শিখিয়ে দিচ্ছি। জানেন, ও জানে আমি কত উৎসাহী টিচার।
হ্যাঁ, দারুণ তো। আমি তো স্যারের থেকে লজিক শিখেছিলাম।
ওকে বারণ করছিল, কার্ন্ডিকায় বারণ করছিল, মনে আছে?
কি
কার্ন্ডিকায় একটু ডিসুয়েট করছিল।
আচ্ছা আচ্ছা, না মনে নেই আমার।
হ্যাঁ, তুমি বলেছিলে। ও বললো যে না, আমি বলতে আমার লেকচার নিয়ে কি হবে, ওটা তো লাক্সারি। হ্যাঁ, বিকজ ডিফারেন্ট, ইন্টারেস্ট ইজ ডিফারেন্ট, কিন্তু নিবে। তুমি সিএসও ট্রেনিং এ যাওনি দিল্লি?
সিএসও ট্রেনিং গেছিলাম, হ্যাঁ
তখনই হয়েছিল, কার্ন্ডিকা ছিল তো।
আচ্ছা, হ্যাঁ কার্ন্ডিকার সঙ্গে ওনার সঙ্গে দেখা হয়েছিল, আমার এক্স্যাক্টলি মনে নেই এখন।
আমি কার্ন্ডিকাকে পাঠিয়েছি।
আচ্ছা আচ্ছা,
কার্ন্ডিকায় বিবি রাও।
আচ্ছা, ও হ্যাঁ ইয়েটাতে, হ্যাঁ।
তুমি
আমি আসলে গত সপ্তাহে হায়দ্রাবাদে সেম টক দিয়েছি ওইটাতে।
হ্যাঁ, আমাকে বলেছে অভয় ভাট।
হ্যাঁ হ্যাঁ,
কালকে জানলাম আমি, ওই বিএলএসপি বাবা মায়ের।
হ্যাঁ হ্যাঁ,
তো ওইখানে কি বিবি রাও ছিলেন?
হ্যাঁ বিবি রাও ছিলেন।
তাহলে আজকে নাও আসতে পারেন।
হ্যাঁ, আজকে মনে হয় না আসবেন, বিকজ ওখানে বিবি রাও ছিলেন, কার্ন্ডিকারও ছিলেন, আরো বেশ অনেক লোকজন, অরূপদা ছিলেন, আরো লোকজন ছিলেন, বিভিন্ন লোকজন ছিলেন।
লোকে ঢুকছে তো।
হ্যাঁ,
question? No, any question? Director? No. Director join করবেন। তাহলে জিজ্ঞাসা করুন, তাহলে আমি জিজ্ঞাসা করে নিন।
Please verify once this Zoom passcode. I have sent it to you once again.
Yeah.
Internet, there is some kind of issue. Can I tell him or we should wait for 2 minutes? I'm requesting Professor Srivastava to introduce.
I'm coming to it. So, I'm sorry, Saurabh, our director is not able to join due to some technical problem. So he was very keen to introduce you. So now he has requested me to introduce you to the paper, to the audience. So, is it going? It's good. Okay. So it's a very, I'm personally very pleased to welcome Professor Cao Chatterjee to this Meghnad Saha Endowment talk. Personally, because I have taught him at IACS, and I am very proud of that. And currently, Saurabh is a professor of mathematics and statistics at Stanford University. Before this, he also had faculty positions at University of California, Berkeley, and Courant Institute of Mathematical Sciences, New York. He got B.Stat, M.Stat degrees from ISI and did a PhD from Stanford University under a very colorful mathematician, Percy Diaconis. He has a varied areas of interest. And I think probability theory is the main, statistics, mathematical physics, analysis, and PDE. And he's considered to be one of the most exciting young probabilists at the moment. He has won, due to his great contribution, he has won many prestigious awards and recognitions. This will be too long, so I will just mention only a few. He is a fellow of Institute of Mathematical Statistics. He was awarded Sloan Research Fellowship in Mathematics. He was an invited speaker at International Congress of Mathematicians held in Seoul in 2014. And recently, very recently, he is awarded prestigious Infosys Prize in Mathematical Sciences for his groundbreaking work in probability and statistical physics. There are other awards, but I think I think the most prominent one is for which people were talking in IXI, that is why I'm saying Line and Michael Loeb International Prize in Probability. Now, I will not take any more time already, so he had fantastic publications. So now I invite Saurabh. By the way, the title of the talk of Saurabh is, sorry, I'm calling him Saurabh because I'm used to calling him Saurabh all the time. So the title of his talk is Some Recent Progress in Yang-Mills Problems, which is one of the 6 millennium problems posed by Clay Institute. So Saurabh, please, over to you.
Okay, thank you, sir. Okay, so I'll share my screen. Let's see if I can do that. Let's see. Okay, is this working, the share screen? Can everybody see my screen, the Yang-Mills?
Yes.
Okay. Thank you. So, so I'll talk about some recent progress in the Yang-Mills problem. So I'll start from the very basics. I'm not assume anybody knows anything about it. So, so to understand the origin of Yang-Mills theory, let us start with Maxwell's equations of electromagnetism, where it begins. So these are equations governing the evolution of an electric field interacting with a magnetic field. So there's an electric field, there's a magnetic field, and they evolve together. And they are parameterized like this. So this is electric field E, which is E1, E2, E3. It's a function of space and time. So at each point in space and time, there is a vector, 3 vector. Okay, so it's a vector field. There is also a magnetic field, and they evolve over time as follows. So this is in space, and the evolution over time is given by this set of 4 equations. So these are Maxwell's equations, and this is what Maxwell discovered, that electric and magnetic fields jointly evolve according to these equations. So so these seem kind of quite arbitrary. Where do these equations come from? It's just a set of 4 equations, and where do these things come from? So instead of these fields E and B, consider a single field on R4 on the full space-time, and here it's a 4 vector at each point of R4. So each AI is a map from R4 into the imaginary axis. This field A is known as a gauge field. Okay. And then you define the curvature form of this gauge field as follows. So Fjk is del Ak del Xj minus del Aj del Xk. So you define this curvature form. So at each point in space and time, you have a 4x4 matrix given by these Fjks. Okay. And then you define your electric and magnetic fields from this. So you start with this gauge field, and then you define E and B from this matrix. So this matrix F, you can see from the definition that it's a skew symmetric matrix, and so there are 4x4 skew symmetric matrix. So there are 6 free entries, and you define electric field as a first, the 3 elements on the first row, and then the rest of the things you define them is the magnetic field. And note that from this definition, this E and B are real fields. Okay, so so you can just, let's say you just define it like this. So you start with some gauge, a single field, this A on R4, and define E and B like this. If you define it in this way, then it can be easily checked that the first 2 equations of Maxwell that I wrote down are satisfied for any gauge field A. So this is called a Bianchi identity. So this is satisfied for any gauge field A. Now, what about the other 2 equations? So you define an action like this. So you define SA to be this. So minus the integral over R4, Fjk x squared summed over all j and k dx, and assume that this integral is finite. So then this is non-negative because these are imaginary numbers. So when you square them, you get negative. So you put a minus sign here. So this is a non-negative functional on the space of gauge fields. And suppose we want to find a local minimizer. So you want to solve a variational problem. Okay, and the Euler-Lagrange equations are precisely this 3rd and 4th Maxwell equations. Okay, so so this is sort of just a reformulation of the problem. So you originally, your Maxwell had these equations for the evolution of electric and magnetic fields. Now you take some abstract thing called this gauge field A, and you obtain the magnetic and electric fields from that. And then you see that those equations are now somewhat more systematic, that the first 2 come just from the definition, the 3rd and the 4th come from minimizing this certain functional. And so you get this. Now, where does this come from? So, So Maxwell's equations, a priori, they look quite strange and arbitrary. Hermann Weyl came up with this gauge theoretic formulation, and this puts Maxwell's equations in the framework of Lagrangian mechanics. So what it does is that in Lagrangian mechanics, a physical system attains a state that minimizes the suitable action. Okay, so here for the electromagnetic field, the action is given by the function S from this slide. Now, the natural question is there a one-to-one correspondence between this gauge field A and this pair E comma B? Okay, so you have this gauge field, which is this abstract object, and you have this pair electric and magnetic fields, which is a very real thing, which you can actually measure in experiments. So is there a one-to-one correspondence between these two things? So I showed you how to obtain this pair EB from A, but can you go backwards? The thing is, it's not. And there's a whole class of gauge fields corresponding to a single pair EB. So this is the origin of gauge equivalence. And we'll come back to this later on. So there is an explicit description of all the gauge fields that give rise to a single pair of electric and magnetic fields. Now, this gauge field is not a physical object, but it's just a conceptual one. The equivalence class of all the gauge fields corresponding to a single pair of electric and magnetic fields is the true physical object that we are interested in. Okay. So this is sort of the beginning of gauge theory, that you have these fields which are physical objects, but then you define in the background. So if you start directly with the pair EB, it's not clear how to put it in the framework of Lagrangian mechanics. But if you sort of go up and define some abstract gauge field up there, then you can define an action, and you can say that the field that minimizes that action is what you see in reality, and then the pair EB that you obtain from that will be your electric and magnetic field. So this was Hermann Weyl's contribution. So any questions until now? You can unmute and ask if you have any questions. Okay. So this is the beginning. Now let's generalize this. So you have this field A from R4 to 4 tuples of imaginary numbers. So instead of that, you can consider a field whose components are this G valued, where this is the Lie algebra of some matrix Lie group, some compact Lie group, subgroup of the interior group. So this, you can consider A to be a map from R4 into G to the 4. The previous case was for G equals U1, for which the Lie algebra is just the imaginary axis. That's the Lie algebra. But you can generalize. So you can take any Lie group and you generalize that. And in that case, if this is if this is not a commutative group, then you define the curvature form in this way. So you have the earlier curvature form plus this commutator. Okay. So again, you get a 4x4 array of elements of the Lie algebra, and then you define the Yang-Mills action the same way. And then you note that this is again non-negative because again, these are skew Hermitian matrices and so on. So everything fits together. So there is a generalization of the thing that I showed you. So instead of having a field where at each point of R4 you have a 4 tuple of imaginary numbers, now you have a 4 tuple of Lie algebra elements, matrices. Okay, and then you define the action in the same way. Okay. Now, why this generalization? There is a very good reason. So it's not just for mathematical curiosity. So why generalize? There are 4 fundamental interactions of nature. One is electromagnetism. These are the interactions between electric fields, magnetic fields, and light. Then there is a weak force, which is describes interactions between subatomic particles that cause radioactive decay. And then there's a strong force, these are interactions between quarks that hold them together to form protons and neutrons. So quarks are things that build protons and neutrons. And then there is gravity. So this is somewhat this popular science thing that everybody knows, that there are 4 fundamental forces of nature, and 3 of them have been unified by quantum mechanics, and the 4th one hasn't been yet. So the unification is as follows. The standard model of quantum mechanics gives this amazing unification of the first 3 interactions. And what it does is, what it says is that if you go to the gauge theory framework, replace the group U1, which gives us electromagnetism, you replace it by SU3, then you get the strong force. And if you replace it by SU2 cross U1, it gives a combined theory of these electromagnetic and weak interactions. Okay, so it's, no one knows why this is true, but it's just something that people have realized, over the years. Many people have been involved in building this, and there are other things in the standard model. There are particles, which I'm not talking about. There is matter, the Higgs boson, and there are fermions and all that. So I'm not talking about any of that, but just the fields, the force fields that you have. are obtained like this. Okay, so that's it's just mind-boggling somehow how this you replace this U1 by this other group and you get the strong force, and it's not clear why this is the case. So now what I described are just classical equations. So Maxwell's equations are classical in the sense that they present a deterministic evolution. The quantum mechanical world is random, as we know. So roughly, very roughly, this is what goes on. In the Lagrangian formulation of classical physics, we assign an action S gamma to each possible trajectory gamma of a classical system. The system follows a trajectory that minimizes the action. So this gives you Newton's equations of motion. So in particular, Maxwell's equations can also be thought of in that context, like Newton's equations of motion. It's the same principle. Now, there are various ways to go to quantum mechanics, and one is Feynman's path integral quantization. So roughly speaking, what it does is that it puts a complex measure with density proportional to e to the minus I over Planck's constant times S gamma on the space of trajectories, where this h bar is Planck's constant and I is square root of -1. And this leads to Schrodinger equation. And when h goes to 0, the idea is that the measure concentrates on the action minimizing trajectory, because far away from the minimizer, there will be huge cancellations due to rapid oscillations. And that's what will cause the whole thing to concentrate on the minimizer. And Feynman has this little popular science book where he gives great explanations of why you see yourself in the mirror in a certain way by these cancellations. It's not because what we learn in school that light goes like this and reflects like this. It's because every other path sort of cancels out, and that's what he says. So you have these cancellation, and this is very hard to make rigorous. As you can imagine, these are oscillatory integrals in function space, so it's mostly not rigorous yet. Okay. So Euclidean field theories. Okay, this is how the physicists actually work with these. So what you do is you remove the I in the exponent. So this gives a probability measure. So as soon as you remove the I, you get a probability measure, and becomes or should become more manageable. So these are called Euclidean field theories. And often the physicists consider it enough to study Euclidean field theories because they obtain results, they do calculations, and then they get the results of quantum theories by what they call analytic continuation. And again, this is all very hard to justify mathematically, but this is what is done. Now, this Euclidean field theory, so this is where my interest in this area comes in. These are natural objects for probabilists. So we'll just study these Euclidean field theories. So you have e to the minus some constant times S gamma, where S is the action. So this is what we will try to study. Okay, so Euclidean Yang-Mills theory. So recall that G is a compact Lie group containing UN for some n, and this Gothic G is the Lie algebra. And the script A is a space of G connections in R4, namely the set of all functions from R4 into the Lie algebra raised to the 4th power. So all 4 tuples of Lie algebra elements assigned to each point in R4. And then there's the curvature form F and the Yang-Mills action SYM as we define. So heuristically, what physicists would say is that a Euclidean Yang-Mills theory in R4 is a probability measure on the space of connections with density proportional to e to the minus beta times the Yang-Mills action, where beta is some parameter which can vary. And this hypothetical object has also been sometimes been called the Yang-Mills measure in the probability community. So construction of this measure is a key step in the solution of this Yang-Mills existence problem, which is still open. And it's one of the Millennium Prize problems. I forget 6 or 7, but the Millennium Prize problems, and there are many steps to solving this, but this is a key step to construct this measure, okay, or make sense of this. So it's not clear. So when I say density, it's density proportional density with respect to a Lebesgue measure in the space of connections, and this is what doesn't make any sense. What's the Lebesgue measure in the space of connections? And then there are many other issues, trying to make sense of this. Okay, any questions until now? Okay. Yeah.
If there is a singularity in the field, so whether it is electric field or magnetic field, so how this generalization for the gauge invariant study or formation of equation will remain valid?
I mean, what do you mean by singularity? Like what?
Yeah, I mean the force field. You talk about the magnetic field or electric field. And I know there are field created in the molecule, which are called, it's a coupling between the electronic state, and that could be singular, and they exactly follow the Yang-Mills field. But since whenever there is singularity, you need to bring the Cauchy's residue theorem to take it out from the equation of motion to show the validity of Yang-Mills theory. So
Yeah, so there are many hurdles to this. So in 4 dimensions, we really don't know how to construct these things, and I don't know if it would correspond to the physical things that you're talking about, but you know, there are fundamental difficulties doing this. So in this talk, I'm going to present something in 3D. So in 4 dimensions, there are fundamental difficulties again due to singularities coming in. You know, these. So you know, the mathematics is not very well understood. So that's the thing about this question. And so making sense of this probability measure or hypothetical thing, you know, is what people are trying to do. And that's one of the problems. I'm sure these questions of singularities will come in if anybody makes sufficient progress on this question. Okay, so. So let's talk about gauge transforms. So you take any connection A with this gauge field and any differentiable function from R4 into the Lie group. Okay. Then you can define a new connection in this way. So you define AG using this formula. So this formula is not particularly important for this talk, so you can just look at it and don't have to remember it. So what this does is that it takes a connection and produces new connection, which is called A superscript G, and this is called a gauge transform of A. And each choice of this gauge field, of this gauge transform field of gauge transform, induces any choice of G induces a gauge transform, and they actually form a group. And if A, so we say that A and AG are gauge equivalent. So these orbits that you get from this action, group action, are called the equivalence classes, the gauge equivalence classes. And the space A of G connections is not the physical relevant object. This quotient space, this A quotiented by G, all these gauge transforms, is what is the physically relevant space. And in particular, going back to Maxwell's theory, I told you that you know, 2 gauge equivalence connections give the same electric and magnetic fields. And this is the precise description of all the gauge equivalent of all the you know, the full equivalence classes. So there is this complete description of these equivalence classes, which give the same electric and magnetic fields. So in the case of you know, Maxwell theory, this G would be 1. Okay. So this is one of the things that makes the problem really hard, because this A is a linear space, whereas, you know, as soon as you quotient it out, it becomes a highly nonlinear thing. And so, you know, so that's one of the contributing things in the difficulty of the problem. And we really, what we are looking for is probability measures on this quotient space. Okay. Gauge invariance. So function f is called, f on connections is called gauge invariant if f A equals f A prime, whenever A and A prime are gauge equivalent. A function is gauge invariant if and only if it can be lifted to a function on the space of gauge equivalence classes. So this is clear from this definition. So, so for example, for the Yang-Mills action, this Yang-Mills action S is gauge invariant. So you can prove that. So any physical observable must be gauge invariant. So for example, the reason is that, for example, in Maxwell theory, if a quantity is not gauge invariant, it cannot be expressed as a function of the electric and magnetic fields. Okay. So gauge invariant means that it can be lifted from the space of connections to this space of equivalence classes, and the equivalence classes are the physical objects. Okay. So in Maxwell theory, if a function cannot be expressed as a function of the electric and magnetic fields, if a function of this underlying, you know, gauge field cannot be expressed, so then it's not a physical thing. Okay. The most important gauge invariant observables are what are known as Wilson loop observables. So we'll talk about them later on. And for the above reasons, any candidate for Yang-Mills measure must necessarily be gauge invariant. We actually have to define a measure on this quotient space instead of the space of connections. Okay, so let me talk about the recent progress, or all the basically the progress that has been, a brief summary of all the progress that has been made. So one common theme in the literature is to look at the problem in dimensions 2 and 3 instead of 4. And that's mainly for mathematical convenience, because 4 is the dimension of space-time. But we cannot really handle 4 so well. So let's look at dimensions 2 and 3. So all that we have discussed until now have analogous definitions in dimensions 2 and 3. So this problem also, the Yang-Mills existence question, also makes sense in these dimensions, although it's not physically relevant. But even physicists look at that, for convenience, not just mathematicians. The greatest amount of progress has been made in 2D. So in fact, we now know how to construct Yang-Mills measures in 2D, so that problem is more or less solved. On the other hand, very few results are known in 3D and 4D. So I'll talk about some of that. Many of these results are for compact manifolds, such as tori instead of the full RD. So there are some fundamental issues in extending it to the full space, but let's be content with doing it on tori. So in the next few slides, I'll talk about some of these known results and present some new ones. In 2D, many authors have contributed to understanding this. So here's an incomplete list, starting from the 80s to very recent. These two recent papers in particular are important. So one of these, the most recent papers of Chevirev, 2019, constructs a space of connections and a probability measure on the space of connections, which can be interpreted as a 2D Yang-Mills measure. And previous works constructed these measures on spaces of observables. So work of Thierry Levy and Len Gross and King and Sengupta, and also Gupta, they did that. And this more recent one, Chandra, Chevirev, Hara, and Shen, they construct a space and a Markov process on the state space such that the unique invariant measure of this process can be interpreted as a 2D Yang-Mills measure. But the problem of whether this Markov process indeed has a unique invariant measure is not known. Okay. So I should say that Chandra et al. They mention in their paper that they have an analogous construction of a Markov process in 3D, but the preprint is not available. Constructions for 3D and 4D theories where the gauge group is U1 were given by Len Gross and Bruce Driver in 1983 and 1989. But for non-abelian, general non-abelian Lie groups, there has been progress of a different kind. So there is this thing called facial renormalization. There is a long list of papers by Balaban between 83 and 89, and then similarly by Federbush, and a different approach of Magnan, Rivasio, and Senior. So none of these papers, however, they construct the Yang-Mills as a probability measure on a space of connections or on some other space. So they're doing something else, which is called ultraviolet stability. And so as far as I can tell, this was not being done. So they do not construct probability measures on spaces of connections or gauge orbits or physically relevant observables. They don't do that. Okay. So here is the main result. It's joint work with my student Sky Cao. In this recent preprint, we give the first construction of a 3D Yang-Mills measure. So we haven't put it in our archive, but it's coming very soon, maybe by the end of the month. So whereas these previous attempts in 3D and 4D try to pass from a discrete to a continuous limit, we directly construct in the continuum. And just to remind you, this is what we construct. We construct a probability measure on the space of gauge equivalence classes of G connections on a 3D torus with this formal representation. D mu A is Z inverse e to the minus beta times Yang-Mills action of A, dA, where dA is this hypothetical Lebesgue measure on the space of connections. And this is the Yang-Mills action, and beta is the coupling parameter, and Z is some hypothetical normalizing constant. So none of this makes sense a priori, but this is in principle, what we're trying to construct. Okay. So you have the three-dimensional torus, unit torus, and you have a group G, a matrix Lie group, a compact matrix Lie group. And then A is a space of connections. So these are all functions from the torus, 3D torus into three tuples of Lie algebra elements. Okay. And then you want to somehow make sense of this, that you have this hypothetical Lebesgue measure on the space of connections, and you have e to the minus beta times the Yang-Mills measure, and so on. Okay. And if one succeeds in doing this, so we have a proposal, and how can this be useful? So just from a physics point of view, so the physicists usually, what they do is that they do perturbative calculations. Okay, so they do perturbation theory, which essentially means that you take this beta to be very large, going to infinity, and then you somehow do some transformation, expand around the Gaussian fixed point, and then you get some, do some calculations using Feynman diagrams and so on. But there are things in gauge theory, in quantum field theory, which are supposed to be non-perturbative, and like confinement of quarks and so on. So they're very important questions which cannot be answered by perturbation theory. So this is what this kind of construction, if one can handle it, in a good way, one can answer those kinds of questions that are not accessible by perturbation theory. Okay, so there are several steps in the proof. So first step one. So we first reconstruct a probability measure, the same measure but with a cutoff. So we restrict our connections to the set of all connections where the Yang-Mills action is at most lambda. So you take some lambda and you do this cutoff. Okay. And this additional term, this indicator term here, restricts mu lambda to connections which have Yang-Mills action at most lambda. And this we are able to define very well. So we'll see how to define this. Okay, so you have the space of connections, you want to define the measure, but then you restrict yourself to all connections which have Yang-Mills action at most a certain amount. Now, this step is divided into 3 steps, 1A, 1B, and 1C. I'll tell you about all of these. So take A, script A with the space of H1 connections. So this is the smoothness class we take, H1 connections, and there is a reason for that, I'll tell you. On the 3D torus, and G to be the space of gauge transforms that map A into A. And there is a more precise description, but I'm not going to that here. Then you consider the weak H1 topology on this space. So you have this H1 connections, and you can consider the weak topology. And then you take its push forward to the quotient space by the quotient map. So recall that the Yang-Mills action lifts to the quotient space. Let omega lambda be the set of all elements of this quotient space with action less than or equal to lambda, and endowed with the same push forward of the weak H1 topology. Okay, so this is the first step. There is a very well-known weak compactness theorem of Uhlenbeck from 1982, which shows that this omega lambda is sequentially pre-compact. Okay, so you take any sequence of elements in this subset of the quotient space, you will find a weakly convergent subsequence. And weakly convergent here means, since it's in the quotient space, it means that you will be able to find this subsequence and gauge transforms, a sequence of subsequence of gauge transforms, so that if you apply this gauge transforms, you end up having a limit. Okay. So anyway, I don't have time to talk about the details, but there is this famous theorem which gives you this. Now, by the Sobolev embedding of H1 in L4, it follows that omega lambda is sequentially closed. So you can prove using the Sobolev embedding theorem that this omega lambda is sequentially closed. Combining, we get that this omega lambda is sequentially compact under the weak H1 topology. Okay. So this step does not work in 4 dimensions because this theorem, this weak compactness theorem, the way we are using it works only in 3D. And the Sobolev embedding of H1 in L4 also works in 3D, but not in 4D. Okay, so these things break down in 4D. So we'll have to figure out how to do something in 4D. Okay, so in step 1A, we showed that this omega lambda is a sequentially compact space under the weak H1 topology. In the step 1B, we show that this is metrizable. So combining the two things, we get that this is a compact metric space. So how do we show this? So this is more complex. So for step 1A, we had some powerful results already available to us, which helped us. For step 1B, we need the notion of regularized Wilson loop observables. So let's talk about this. So I haven't defined Wilson loop observables until now. So I have to talk about them, the Wilson loop observables, and also what is meant by regularization. Okay, so first, let's say what's the holonomy. So let A be a smooth G connections. So now not H1, smooth G connection on this torus. And then you take a piecewise C1 closed path L, and you define an ODE.
Can I ask a question at this point?
Yeah.
Can you say a word about why this is actually compact? Formally, this is an infinite dimensional quotient. So I'm somewhat puzzled how it becomes. This is a kind of bounded part of an infinite dimensional quotient.
Yeah.
It become compact.
Yes, so it becomes compact because of the following reasons. So this the reason is that when you are saying omega lambda, remember, is the space of all gauge connections which have bounded Yang-Mills action.
Right.
So as soon as you have bounded Yang-Mills action, what Uhlenbeck is essentially saying is that there is a way to, so the connection may be very rough, but there is a way to somehow do a gauge transform in it to make it sufficiently smooth. You see, so that's the thing. So that's why it becomes compact. So
I see.
So
the boundedness of the norm of the curvature actually constrains in the quotient this to a sort of finite dimensional subspace. Is that the intuition?
Yeah, something like that. So you can make this rough connection sufficiently smooth. You can actually get a bound on the H1 norm, uniform bound. So if you have let's say you have a sequence of connections with bounded curvature, then you can do gauge transforms to each of them so that the whole sequence becomes bounded in H1 norm, something like that. And then it becomes, then you can extract a convergence subsequence, weakly convergent subsequence.
Okay.
So this is
does
how
work in the abelian case?
Yeah, it works in both abelian and non-abelian case. The thing is, it doesn't work in 4 dimensions. Okay, so the Yang-Mills action is the L2 norm. So in 4 dimensions, you can do some LP norm for smaller p of the curvature, but you cannot do the L2 norm of the curvature. So somehow it just breaks down in 4 dimensions. It just barely doesn't work. 4 dimensions. Okay, so holonomy. So you have this smooth gauge gauge field, G connection, and then you define an ODE on the space of matrices, so elements of G in this manner, and then it exists in unique and so on, and then HB, sorry, this should be H1. H1 is called the holonomy of the loop. So basically, you don't have to look at how this is defined. So this is essentially what is known as a path ordered integral. So what a connection does is that it changes the coordinate system as you go around a loop. And so if you start with the identity matrix, the identity matrix is a parallel transport with this gauge transform with this connection. When it comes back, it becomes something other than the identity. That's called holonomy. So anyway, this is a formal definition. So given any piecewise C1 loop and any connection, a smooth connection A, you can define a holonomy. And then Wilson loop observables are defined as follows. So these are very important in physics. Let L be a piecewise C1 closed path, and let chi be a character of G. Take any smooth G connection A. The Wilson loop observable WL chi of A is defined as follows. It's chi applied to this holonomy around the loop. So the connection gives a holonomy around the loop, which basically, given any loop and any connection, you can produce a group element, combining these two things. It's a parallel transport, and then you define, you apply the character chi to that, and that gives you a complex valued function, okay, on the space of connection. So that's called a Wilson loop observable. And the nice property of Wilson loop observables is that they're gauge invariant. You can prove that if you apply a gauge transform to a connection, the Wilson loop observables don't change. So therefore, they lift to functions on the quotient space. Okay, so the Yang-Mills heat flow. That's the next thing. So now we have defined Wilson loop observables. We have to now say how are you going to regularize them. So there's this notion of regularized Wilson loop observables. So given a G connection A on the 3D torus, recall that the curvature form is defined like this. Then the Yang-Mills heat action is the following nonlinear PDE that describes the evolution of a time-varying connection AT. So suppose you have a sequence, you have a whole bunch of connections for each time t, and then you do an evolution in time, and this is the equation, the Yang-Mills heat equation. So this is del Aj del t, and then this is del Fjk del xk. So Fjk itself is a nonlinear function of A, and then there is this commutator again occurring here. So you have third powers of A somehow three things, so it's a complicated equation. And there's this, now this classic result of Roder from 1992, which shows that for a three manifold without boundary, such as the torus that you're working on, so we have a 3D manifold, the Yang-Mills heat equation has a unique solution over all time when the initial condition is in H1. So this is exactly what we need somehow. That there is.
So formally, is this the gradient flow of the Yang-Mills, the L2 norm of?
Yeah, it's the gradient flow of the Yang-Mills action. Yeah, exactly. That is what it is. Yeah, and okay. So, so in particular, when the group is commutative, it all becomes very nice. It just becomes, like the ordinary heat flow. But when you have a non-commutative group, then it becomes highly nonlinear. And this is a difficult paper. And so now, how do you regularize by the Yang-Mills heat flow? The main idea behind the Yang-Mills heat flow is that it smooths connections just as ordinary heat flow smooths functions. The additional property of the Yang-Mills heat flow, which makes it very suitable for gauge theory, is that if you have two flows B and A, so that B0 is a gauge transform of A0, then for every time t, Bt is the same gauge transform of At. So the Yang-Mills heat flow lifts to a flow on the quotient space. So that's the nice thing, that it will not happen if you just smooth using the ordinary heat flow. So the Yang-Mills heat flow lifts to a flow on the quotient space. And this has become very popular. So physicists have done a lot of work starting with these two papers. And there's a large literature on this now, smoothing this, regularizing gauge connections by the Yang-Mills heat flow. So now how does it smooth? It's not completely trivial how it smooths. So suppose if you start with the H1 connection, it does not necessarily mean that At is in some smoother class. That's not true. What happens is that it smooths in the following, in a very indirect way. So there is this trick discovered by various people, Zwanziger, de Turk, Donaldson, Sadoun, in various years. So sometimes I've heard it called as Zwanziger de Turk trick, or sometimes ZDS trick. So using these tricks, which I'll not tell you what it is, it's basically replacing the Yang-Mills heat equation by some other equation and then working with that. It was shown in this recent paper of, relatively recent paper of Charalambous and Gross, that if you start with an H1 connection, then for a small time, sufficiently small time t, there is a gauge transform GT, which if you apply to AT, then it becomes C infinity. Okay, so it's not as if AT itself will become C infinity, but there's something in the equivalence class that will become C infinity. And then there are various estimates also. So this is not just this, there are more, you can get some bounds and so on. And this is only for compact 3D manifold. So it doesn't, again, there is no extension to 4 dimensions. So combining this with the global existence result of Roder, we can arrive at the same conclusion for any time t. And this allows us to define this regularized Wilson loop observables. So remember, Wilson loop observables are only defined for smooth connections. So they're not defined for H1 connections. So what do? We take a time t positive. We define WL chi t of A as follows. We take AT to the GT, where GT is this transform which makes it smooth. And then you apply WL chi to that. And you can show that it's well defined and so on. So this is what's known as regularized Wilson loop observables that many people have been working on. Now we are ready to prove the metrizability of this omega lambda. So recall that omega lambda is set of all elements of this quotient space with the Yang-Mills action bounded by lambda. By a result of Sengupta from 1994, the collection of all the Wilson loop observables uniquely determines the smooth connections up to gauge transform. So there is this one-to-one correspondence. And using this and the continuity of the Yang-Mills heat flow, we can show that not only the collection of all the Wilson loop observables, but a subcollection, countable subcollection of all regularized Wilson loop observables uniquely determines the H1 connection, okay, up to gauge transforms. And using the results of Charalambous and Gross in sequential compactness, we show that this one-to-one map that takes omega lambda to this above countable subcollection of regularized Wilson loop observables is a homeomorphism if we put the weak H1 topology on the domain and the product topology on the range. Okay, so if you do this, then we get, so this is the proof of metrizability. So you have this space omega lambda, then you define this regularized Wilson loop observables using this Yang-Mills heat flow, and then you map a connection to this countable collection of regularized Wilson loop observables, and then you can prove that that's a homeomorphism between the two topologies, and that makes this metrizable. Okay, as soon as you have a countable collection, you get metrizability automatically. So this implies that this weak topology is metrizable. So combining these two steps, it follows that, so step 1a says that omega lambda is sequentially compact. Step 1b says that it's metrizable. So it's a compact metric space. In particular, it's a Polish space. And now we construct a sequence of well-defined probability measures on our script A, which in principle approximate mu lambda. So that is not very hard to do. So you have this kind of abstract thing, but there is always some discrete approximation to that. The push forward of this sequence gives a sequence of probability measures on this omega lambda. And the sequence is a weak star convergence subsequence by Prohorov's theorem. Okay, because we now have a Polish space, so we have Prohorov's theorem on Polish spaces. And any subsequential limit is a valid candidate for mu lambda. So we do not prove uniqueness. We're not able to prove uniqueness. So this completes step 1. This constructs the Yang-Mills measure restricted to this omega lambda with this restricted space. Okay. Okay. Any questions about this?
So your sequence of probability measures on A, they are all supported on the inverse image of omega lambda?
Yeah.
Okay.
So I construct the restricted measure by, so they're all supported on the inverse image of omega lambda.
Okay, thank you.
Okay, so this is the first step. The second step is a bit more abstract, and the abstraction of this thing makes it hard to extract useful information, but it may be possible. So by step 1, we have a measure mu lambda and omega lambda for each lambda, and in principle, what we want to do is that you want to take lambda to infinity, okay, and you want to get a limit. You want to remove the cutoff. So it's sometimes called ultraviolet cutoff in the physics literature. So construction of this is step 2 of the proof, which will break up into steps 2a and 2b. Okay, so 2a is that we first embed this quotient space in larger space. So this is like, so in probability, we construct random distributions as limits of random functions. This larger space is obtained by first replacing the weak topology by the topology generated by the collection of all regularized Wilson loop observables. And under this topology, this quotient space is homeomorphic to a subspace of compact Hausdorff space. So this we can show. And so taking the closure gives a compactification of this space, which we call script C. And next we show that this new topology is the same as the old topology in each omega lambda. So that's important that you have that. And this is achieved by showing that omega lambda is homeomorphic to the same metric space under both topologies. So we constructed this metric space using a countable subcollection of regularized Wilson loop observables. We showed that omega lambda is homeomorphic to the space under the weak H1 topology, and then we show that it's also homeomorphic under this new topology. And recall that this is a compact metric space, and any probability measure on a compact metric space is automatically a regular measure. So I'll not go into the definition of regular, but let's assume this. So it's known that it's a regular measure, and from this it follows that mu lambda is a regular measure on this compactification of the quotient space. So you have this quotient space A/G, and it has this compactification C. You can think of C as a space of generalized gauge connections, and mu lambda becomes a regular probability measure. And there is an abstract version of Prohorov's theorem, which implies that a net of regular probability measure on a compact Hausdorff space is a weak star convergence subnet. So we can no longer work with sequences, but there is a weak star convergence subnet as long as you can prove that the probability measures are regular. And the fact that these are compact metric spaces, even within the supports of this measure are compact metric spaces, even within this very abstract space script C, helps us do that. Okay. And this gives us our candidate for the Yang-Mills measure mu on the 3D torus, thereby finishing this construction. So again, it's a subnet limit, so we don't know anything about uniqueness. But it makes complete sense somehow that you have this measure on this space of generalized connections. And this is what people expect, that you don't expect to have a probability measure on the space of nicely behaved connections, but rather some kind of distribution of connections, something like that. So that this is what people expect. Okay, so this is the full construction, omitting all the details, but just an overview. So final remarks. So we constructed our Yang-Mills measure mu on a space script C, which is a compactification of the gauge orbit space under a certain topology. So elements of C can be thought of as generalized connections. Now, the question is, what are continuous functions on C? What are measurable functions? Well, we don't know the list, but at least we know that regularized Wilson loop observables are well-defined and continuous on this abstract space. And on the restricted space, we can actually define Wilson loop observables without regularization by taking some L2 limit. So this is not possibly possible on the full space. Now, as I said, this construction uses very general arguments, especially the second part, and also the first part, very general arguments. There are many desirable properties which remain unproven. So, so we are working on actually figuring out this limiting distribution, this mu explicitly in some cases, but that's ongoing work, especially if the gauge group is U1, I think it may be possible. But anyway, we give a list of properties. So it is sort of akin to, for those of you who have a probability background, if you want to construct Brownian motion, there is this very general argument which gives you construction on the space R to the 0 infinity with the product, sigma algebra. And then you have to prove something like Kolmogorov-Chensov theorem to get that the Brownian motion actually has a continuous path. So this is the kind of thing that we'd like to prove, that you have this construction, but then the objects that you get, the random connections or random whatever, generalized connections that you get have nice properties. Okay? Extending to 4 dimensions is the main goal. We are able to do in 3 dimensions, but we would really like to do in 4 dimensions. And all of these results that I used, Uhlenbeck compactness, the Sobolev embedding that we used, and then the Yang-Mills heat equation, properties of the Yang-Mills heat equation, regularization, everything just is in 3 dimensions. So none of those things extend to 4 dimensions. So it's a challenge. Okay, so thank you. That's all.
Yeah. Actually, a few questions. Huh?
Hello, may I ask a question?
Yeah, please.
Suppose you have a connection which is smooth and is taken into another smooth connection by a gauge transformation, which is not necessarily smooth. I suppose that can happen, yeah?
Yeah, that can happen. Yeah.
And in that case, can you have a smooth gauge transformation which will take the first into the second, necessarily?
I don't know the answer to this question, no.
Actually, that will generally be the case because the composition of the two will fix the gauge field.
What is the automorphism group, isotropy group? It may be very large even for a smooth connection. If you take all gauge transformations which are not necessarily smooth, there may be many which will fix it.
Typical gauge field has very few automorphisms.
So we do have some degree of smoothness. The gauge transforms we are considering, I did not say that explicitly here, but they are in H2. So we are essentially taking H2 gauge transforms so that they send H1 connections to H1 connections. They have some degree of smoothness.
Next question, please. And kindly identify yourself, one who is asking the question.
So this is Ramdas, can you say something about how, anything at all about asymptotic freedom? I mean, your beta, how your construction changes with beta? Do you have any control at all on that?
No, so this is what I was talking about, the properties of the measure. So we use very general arguments. So the properties, understanding the properties of the measure is completely left as a completely different question, like whether you would have continuity, whether you would, what would be the small scale structure of these things, so that all of that, so our construction just gives you the measure, okay, so which wasn't there before. So we give the measure, and then the next step is to try to understand the properties of the measure, and that's that we separate out as a separate question.
For example, is there some hope that you can compute on your omega lambda, for a fixed lambda, say the 2-point function of the curvature or some function thereof.
Yeah, so this is what we are trying to do, at least for U1. So when the gauge group is U1, it's a simple situation, and so it may be possible to do that because we now have a very specific prescription for constructing this measure. Earlier, what used to happen is that people used to and still it's the most popular approach, that to start from lattice gauge theories and work towards building a continuum limit. And I have worked in lattice gauge theories also, and they're very difficult to handle, and very complicated and very difficult to handle, and we really don't know. Here, what we have is that we start with something directly in the continuum. So what we do, our discrete measures are basically truncated Fourier series. So you take Fourier series and you truncate them, and then you put a measure in front of them. So it may be possible to carry out some calculations, the kind of things that phases do, all these Fadeev, Popov ghosts and all that. So, it may be possible. I mean, it looks at least feasible that one can approach that, which, was very hard to do anything like that with lattice gauge theories. But, right now it's only speculation. So I don't know if that will actually turn out.
Okay.
One more question, if there are any.
Okay, I have one more question. This is Nitin Itsure. If your spaces have some kind of holomorphic structure, they are somehow related to varieties, and your gauge group can be complexified into a complex linear algebraic group, then this A mod G might have interpretations as some varieties, moduli varieties, etc. So are there examples of this kind where all this becomes simpler and very geometric?
Yeah, so there are all these exactly solvable models that people work with, this things, Seiberg and Witten and all that, so that if you put in, some supersymmetry or something, you can get an exactly solvable model, and you can do a lot of very nice math. And, I'm not particularly familiar with that, but, so that's, you can get a lot of nice mathematical structure. And, there are these papers of Witten and, I'm forgetting the name of the co-author, where they say that they're even if you put in sufficiently nice things, the supersymmetric structures, you can get correspondence with some connection with the geometric Langlands program. So there is some conjecture. So there are various conjectures about that, which I think have not been made rigorous at all.
Yeah, what is written there? Can you see the chat box, Saurabh?
Yeah, I can see it's written in quantum chemistry from 1975 onwards, while solving Schrodinger equation, the make use of the UIM theory for n-dimensional sub-Hilbert space well statistical molecular field. Yeah, it's a long thread.
Is it a question?
No, it's a suggestion.
It's a suggestion. Okay, then I think I'm sorry, I also have a class just now. But many thanks, Saurabh, for giving a fantastic talk. And at the right place where a lot of physics happens, and now mathematics is also beginning. So let's hope. And we get very bright students in here, science students.
Yeah, okay. No, thanks a lot. Yeah, it's nice to see you, and it's really nice. Thank you.
Okay.
I'll stop the share.
Okay. ঠিক আছে, আমার ক্লাস আছে। হ্যাঁ, আমি